Now, before we start, I just want to lay out a bigger picture, and then slowly we will work our way to the types of the particles that we are going to learn here. Okay, so it all started from according to the theory of the Big Bang. Okay, it says that like very long time ago, like 13 billion years ago, it all started with a point. Okay, and then this point is like very dense. Okay, it's very dense and very high energy that it slowly grew a little bit larger over time, and then at one point that it explode, and there goes the Big Bang, right? So it is a very dense ball of energy before the explosion, and after the explosion, right, it creates all kinds and all forms of particles in the universe that we see today. Fast forward to today, which is after about 13 to 14 billion years. Today we discover many types of particles, the proton, the neutron, and at first we believe that the proton and the neutron, they are the smallest particle, like the electron. We go the subatomic particles that we learn: electron, proton, neutron. They are the smallest unit of particle. But then over the decades, they found that there are actually a lot more particle out there that haven't been discovered. Okay, so what is the total amount of particle discovered to this day? There are about 400 particles, a total of 400 particles that we have discovered up to this day. Out of these 400 particles, right, 99% of the 400 particles, they are unstable. What does it mean by unstable? That means that they only exist for a short fraction of a second. They cannot stay there very long one. This unstable particle happen only like nanosecond, then it will disintegrate, it will break down into other form of particle. So they keep changing into other forms of particle. So that is one of the reasons that they are very hard to discover, very hard to find them, because a fraction of a second, then they're gone already, right? Those are unstable particles. Now, only 1% of these 400 particles, they are stable, meaning that they can sit there without changing into something else. Okay. Now, the thing is, how do we discover 400 particles? How do we discover so many particles? Like, what is the method behind it? The scientists, they did, after the Rutherford experiment, the alpha scattering experiment, okay, they did a lot of experiment to find out the answer to the question, where is proton the smallest unit? The chemists, they have, after the discovery of the proton, they have already compromised. They agree that, okay, we are going to take proton as the smallest unit. Then they draw a line over there. They drew a line, and then they say, okay, we are going to stop discovering this one. Then we just stick to proton as the smallest unit. And then they come up with all types of model. Then you have the atomic model, right? You have the nucleus made of neutron, proton, and electron. Okay, so chemistry only until there. There's no chemistry beyond that. So the physicists, then they are more ambitious. They say, okay, I want to know more about proton. What is the particle that makes up proton? Is proton the simplest unit, or is there more particles inside the proton? Can I break proton down into smaller particles? Okay, so the physicists, then they continue this discovery. How do they discover? They use a method, a very simple method, that they create the same condition of the Big Bang. What do I mean by that? The Big Bang, it has a lot of energy at first, and then there comes the explosion that creates matter. So matter and energy, they are related, right? You have the equation E mc squared. The amount of energy can be converted to matter. The matter can be converted to energy. They are related. So from the Big Bang theory, right, the huge amount of energy after the explosion, after the collision, that creates matter. So the scientists use this same idea. They say, okay, we need to accelerate the particle to a very high energy, high speed. First, I need to speed up the particle so that it moves very, very fast with very, very large energy. I can simulate the condition of the Big Bang. Okay, I can recreate the condition of the Big Bang. And then what I'm going to do is I'm going to smash this particle. If I have two very high energy particles, I'm going to smash it. And then when I smash it, then there is an explosion, there is a collision, and maybe we get something out of that. We get a new matter, we get a new particle. We don't know, right? So the main idea behind it is that they are going to smash particle. They are going to make particle collide with one another. Okay, first they need something to accelerate the particle to a very high energy, high speed. Okay, when I say particle, it's like proton. They accelerate proton to very high speed, and then they will crash this proton together. So that high energy environment, and together with the collision, that creates many, many more particles. And then based on those particles, the product of the collision, they study one by one. Okay, what particle is this? Is this particle discovered before? Okay, this is a new one. Put it in the list. Okay, this is the same one. We just move on to the next one. Okay, there are many millions and millions of particles coming out, and then they study one by one. They found how many in total? So far, 400 particles in total. Okay, some particles, they have not been discovered in isolation. What does it mean? That means they have not been discovered by itself. Like, okay, there's this particle is over here. It is always combined with some other particle. That is what makes it very hard to discover. Okay? Because most of the particles, they cannot exist by themselves. They always exist together with another particle. And some particle, okay, they are only theorized. That means not confirmed that it is not confirmed it exists yet. Okay, for particle like graviton, later we'll look at all these different types of particle. Just to give you an overview of this, like a graviton is a particle, okay, graviton. It has not been proven exists yet, but they believe there's something called this graviton, which is responsible for the gravity of matters around us. Yeah, so from here, so all these people, they say, okay, I'm going to accelerate, I'm going to build something to accelerate these particles, and then I'm going to collide them, collision. Okay, so they built over the decades, they built what? After the alpha scattering experiment, they built this particle accelerator. Okay, it's like a long, huge tunnel. They accelerate particle and then they collide the particle. Over the years, they have built many particle accelerator. With each particle accelerator, it gets more and more advanced. It gets bigger and bigger and more energy. Because if you want to discover all this strange particle, right, you need very high energy. So if you accelerate particle at very high energy, you need a bigger accelerator, right? You need a bigger. The bigger you have, the more you can discover. Satellite, right? So now they're constructing the biggest satellite in the world, and then they want to discover outer space. Same for particle accelerator. Now, here I have a picture. Let me switch to my slide. Here. Okay. On the screen here, you see an image. This is the largest particle accelerator in the world. It is built by the organization CERN, C-E-R-N. What does CERN stand for? CERN stands for, I think is, if I'm not mistaken, it's like European Organization Nuclear Physics. Okay, it is a, like about 40 years ago, they built this organization, and the aim is to study the field of particle physics. Particle physics is just a study of collision. You are basically colliding particle and then see what's coming out. That's particle physics. Okay, if you were to sum up the whole thing, right? So they built this a Large Hadron Collider, okay, which is located in Switzerland, Geneva. Okay, you can see all the Alps here, the blue mountain at the back. This is in Geneva, Switzerland, and you can see the ring in yellow color. The ring, what is that? That is the Large Hadron Collider. That is how big is it. This is the size of it. What is the circumference of this thing? 27 kilometers. Okay, the circumference of the ring is about 27 kilometers. That is the tunnel. That means the particle travel here inside this ring, and it is underground. Okay, it's underground. And how deep is it? This one is about like 100 meter, over 100 meter deep from the surface of the ground. Okay, so they built this Large Hadron Collider. Main is to provide the facility. Okay, they want to provide this instrument for scientists in all around the world to come together and then study this particle physics, right? So this is a picture underground. Okay, so it shows the structure of the tunnel. Okay, you can see the tunnel over here. LHC stands for Large Hadron Collider, and you can see here it shows all this. What is this? CMS, Atlas, and Alice. All these are the control room. I can say control room because this location is where the collision of the particle happened. For example, like this one over here. This is where the collision happened. Oops, let me use a different color. This one. This is where the collision happened. This is another station for the collision. This is another station, and this is another station. You got like 4 stations over here. Okay, how do they accelerate the particle? At first, the particle, proton, they accelerate proton. Okay, like you can see this small ring over here, right? This small ring over here. This small ring over here is to accelerate the particle before they collide it. Okay, that the particle, they move in this ring before being passed on to the bigger ring. So they move here, they accelerate this one, and then they come out from this bigger ring in opposite direction. So one proton go here. Okay, one beam of proton, it goes here, and then the other beam of proton, it goes the other direction. And then they meet at this 4th station. The collision can happen anytime. Can happen anytime, because you are talking about the beam is, how small is the beam? The beam is like, you think of it like a spaghetti, right? It's like the length of the beam is like a spaghetti. And then how many protons are there in that beam? There's so many protons, it's about like 100 billions of protons in the beam, one single beam. That is only the length of a spaghetti, right? And then the diameter of the beam is very, very small. It's like smaller than the diameter of the human hair. That means it's very, very hard to hit for these 2 beams to collide because they are so small, right? How do you collide these 2 beams? It's like you imagine one person shoot an arrow from here, another person shoot the arrow from here, and you're trying to hit the arrow together like that, tip to tip. It's very difficult, right? So that means that when the beam come, they might miss. If the beam miss, then it will go again another cycle and then collide. Okay, it might collide in the next a few cycles. Okay, so the collision can happen any time, and the collision happens at the 4, force station over here. This is where they study the collision. So it's like when the particle hit, they collide, and then many, many things come out, and then they study based on the result. Okay, in this force center, force station here. Okay, so that is basically the LHC. Okay, and the CERN. Okay, you have the CERN logo over here, top left. Right. So now inside looks something like this. The picture on the left, the particle accelerator. Okay, this is inside the tunnel, right? This is the particle accelerator. So it is joined by so many machines. All these machines, they are made of superconductor, all these electromagnet used to speed up the particle. Okay, the magnetic field to speed up all these charged particles. How many machine of this? This is about like 10,000 of this machine joined together. And during the construction, right, there was a flaw to the joint. Like when they join one to the next one, right, the welding joint here, there was a flaw there. So they had to like fix the flaw. So they have to like fix the all 10,000 machine. Okay, so it's a lot of 10,000 machines. You have because of one flaw, you have to fix like 10,000 machines. Okay, so it takes many time, long time to fix it. Okay, that was during the construction of this thing, because when you want to accelerate this thing, right, the path it has to be like very accurate. Okay, because you're dealing with a very small particle. So a slight deviation will affect the travel of the particle. Okay, that is the picture on the left. And you see the picture on the right. This one is at one of the station. Okay, this is where the collision happens. Okay, you see this very large thing. What is this? Because you need a lot of energy to accelerate particle, right? So all this thing is built very big. Okay, to give enough energy for the particle to smash. The bigger the energy smash, the more particle you can discover. Okay? The more particle you can discover. Now, many particle accelerator are built. This is one of the largest one. And this is a very famous one. Why? It's because this one is where all these scientists, they discover a new particle called the Higgs boson. Okay, they discovered the Higgs boson in 2012 in the LHC, in the Large Hadron Collider, in one of the project during that time. In 2012, they discovered this Higgs boson. Why this Higgs boson gained a lot of fame is because the Higgs boson is one of the particle that is responsible for the mass. It's like they believe that all the mass of matter comes from the Higgs boson. Higgs boson is the one that gives rise to the mass of particle. It's like we never ask the question, why do we have mass, right? Mass is just mass. Why do we have mass? They believe that it is because of this, the presence of the Higgs boson. Okay, so this also we will look at different types of particle very shortly. Okay, after this. So this is one of the boson particle. So this one is discovered here, right? Okay, now this one is the image showing the collision. This is inside the collision. Inside the accelerator is where the collision happens. So you can see the two beam. This one, the red one beam of proton here, another beam of proton here, and then they collide. So they want to hit at the exact point. Okay, so if they miss, then they go one round again, come back, and then they collide again. Now, when they collide, this is the image shown on a computer. Okay, so based on all this line coming out, all these are particle. All this yellow line coming out is particle. So you can see the particles, some are deflected, some go straight, okay, some go like a curve shape. Based on the curvature, they can calculate Is the particle having a charge? And what is the mass of the particle? What is the velocity? What is the momentum? Then they can see, is this particle discovered or is it a new particle? Okay, based on all this, they can study this diagram here, right? So these are placed in a field, in a magnetic field, so they can see the interaction with the magnetic field to tell the mass of the particle. So this is another picture of it. So this picture is like where they every day they just look at all these pictures and then they study what is this, what is this, what is this. So the Higgs boson is discovered from this picture, like from all these pictures. Okay, like when they see this one, oh, this one is what is this? Okay, this is the Higgs boson. Okay, do you see Higgs boson here? I don't see any Higgs boson here. Right, so this is how they discovered the Higgs boson from pictures like this. Okay, right. So a lot of particle smash based on all of this, they have categorized, okay, into two main parts. And in the next slide, we will look at the classification of all these particles in the universe. Here I have laid out all the particles. And in this lesson, okay, in your A-level physics, not all you need to know. You only need to know a few, and I will point out the things that you need to memorize and you need to know. So basically on this slide, you see all of the particles, okay? They are separated into two main groups: the elementary particles and the composite particles. Elementary particle is like fundamental particles that cannot be broken down into any further. That is like the base of the base already. It's like your base quantity, okay? They exist by themselves, okay? Cannot be broken down anymore. These are the elementary particles. Composite particles, they are the larger one. They are a combination of the elementary particles, like your base and your derived quantity. So it's like your H, hydrogen, oxygen, they are elementary, and then you've got H2O is the composite. Okay? And the composite particles, they call it what? They call it hadrons. Hadron, H stands for a heavy. These are the heavy particles. They are larger and they're heavier. Okay. Now, for elementary particles, we separate it into two: fermions and bosons. Let's look at fermions. Fermions and boson, right? They both are like a point-like particle. It's like one tiny point. They do not have particular structure to it. It's like just one point. Okay, so the fermion is divided into 6 leptons. Okay, the first group is the leptons, and then the second group is the quark, Q-U-A-R-K. Now for the lepton group, you got 6 leptons plus the opposite, the twin of it. Okay, like 6 lepton, and you have 6 Nd lepton. Okay, so one example of the lepton is electron. Okay, this one is the one that you are familiar with. There are many. Okay, there are a lot. There are a total of 12, but here I just listed one here, the one that we are familiar with. All right, so electron is a lepton. Electron is a lepton. Okay, second group is quark. Now quark is made of 6 quarks plus 6 Nd quarks. So total you got 12. Right? And these are the 3 common examples. Okay, you got the up quark, the down quark, and the strange quark. Okay, up. Each of them, they have their counterpart. You have up quark, you have Nd up quark, and then you have down quark, you have Nd down quark. Okay, so all of this, they have their twin. Okay, so that is the fermions. Okay, the fermions. Now, and then the second one is the boson. Now, the boson is like a special type of particle. How special is it? Because they are mainly, they are the particles that is related to the 4 fundamental forces of the universe. What do I mean by that? For example, like gravity. Where do we get gravity? Okay, they believe that gravity is related to a particle called the graviton. This is the last one over here. It's like the graviton is the one that gives rise to gravity. It's like when the earth is pulling you with its gravity, it's like the earth is interacting with you with the graviton. Okay, so that is what they believe, right? But then graviton is not been discovered yet. Okay, but it is highly possible that they believe that it exists, right? And then the Higgs, now this is the one that I said just now, the Higgs boson, right? The Higgs boson is the one discovered from the Large Hadron Collider. The Higgs boson is the one that gives rise to the mass of object. And then what you see here is the G. The G stands for gluon. Okay, you can think of it like glue. They're like they glue together molecules, they glue together particles. This is like the strong force molecules between particles. Okay, gluon, they believe that this is the one that gives rise to the strong nuclear force that is holding the proton together. Okay? Strong nuclear force. Okay, and then you have the Z boson and then the W minus and W plus boson. These two, right, is the particle that give rise to the weak nuclear force. Later, I'll go into much more detail about this one. This one I'm just giving you a overview. Okay, weak nuclear force here. And then the first one you know, this one is a photon. Okay, photon of light is no mass, only energy. Okay, so if you see the boson, right, they are not normal particle, right? Because these particles are force related. They are like the force carrier. Okay, we'll call it like force carrier. They're related. This one is related to gravity. This one related to strong nuclear force, weak nuclear force, like this. They are the boson. Okay, they are under the boson category. Right. So those are elementary particles, right? So now we go to the composite. Now composite, okay, composite is divided into two, the baryons and the mesons. Okay, for the composite, they won't ask that many, but the thing that you need to know is this one, made from 3 quarks. They will ask this and you need to know this. Like baryon is made from, all baryons, they are made from 3 quarks. Okay, and all mesons, they are made from 1 quark and 1 antiquark. Okay, so you have a lot of mesons. Later, I will show you the list. And the baryons, the most 2 common one that we are familiar. First is the proton. This is proton. And neutron. Okay, proton and neutron, they are baryons. Proton is considered a stable particle. That means they can sit there without breaking down. But neutron sometimes can be stable, sometimes not stable. It is found that the neutron inside a nucleus tend to be more stable than neutron outside of the nucleus. If the neutron is outside of the nucleus, then they are not very stable. How long they can last? They can last only like 920 seconds before they disintegrate. Okay, yeah? Right. Now, next one, we see some of the common examples of the leptons, the quarks, the boson, the baryon, and the meson. Now, quarks is the most often they will ask this, the quark. Up, down, strange. Okay, you have other 3 types of quarks. I will show you in the next slide. But quark is the main, we say it is the building block that makes up most of the composite particles. Most of the composite particles over here, they are made from the combination of quarks. Okay, so we say quark, they are the building blocks of all matter in the universe. because you see baryon is made of 3 quarks, meson is 1 quark and 1 antiquark. Okay, next slide. Right, this one is the list of all the particles. Okay, no need to memorize all. I will tell you which one to take note, right? Just to see the entire picture of it. The same category, nothing has changed. Same category from the previous one. You're just seeing all these particles under each category. Let's start with the lepton. Okay, so electron is lepton, right? We got electron, we got muon, tau, and then you got neutrino, right? So this neutrino is the one that emitted during the beta decay. From our last lesson, we talked about beta decay. When the beta is released, the neutrino also released, right? So electron neutrino, muon neutrino, and tau neutrino. And all of these 6, right? 6 particles here. So you got 6 lepton. What you have as the counterpart, you got 6 lepton, then you have 6 anti-lepton. Okay, so these are the anti-lepton. For the anti-lepton, you just change the charge. All these are negative, you become positive. All this without the bar, we add a bar on top. Okay, the bar means it is the anti-particle. And then we have the quarks. Yeah, this one is the one that you need to take note of. Okay, this one. So quark, all of this, 6 of this. Up, down. These 2 are discovered first because they don't need that much energy. They can be discovered using Small Hadron Collider, Small Particle Accelerator. And then moving to the second one, Strange and Charm. These 2, they are discovered later because these 2, they require more energy. So you build more bigger particle accelerator, then only you can find these 2. And then the last 2 is this top and bottom. Okay, they are the one with the largest energy. So this one I arrange. Top down is like you need more energy to discover going down the list. Okay, now here you need to know the charge of each quark. I will write it at the side. Up quark, each one of them, they have a charge. So up quark is going to be 2/3 positive. Okay, positive 2/3, and I put an E here. This is elementary charge, the 1.6 times 10 minus 19, the charge of the electron. Okay, so the charge of an up quark is plus 2/3. Down quark is a minus 1/3 E. Okay, and then the strange is minus 1/3 E. It's repetitive, it's repetitive. This one is plus 2/3 E. And the top is plus 2/3 E. This is minus 1/3 E. Okay, you better if you can exchange the place for the charm and the strange. If I exchange the place between the strange and the charm, then you can see the charge goes like positive 2/3, negative 1/3, and then we have positive 2/3, negative 1/3, and then positive 2/3, negative 1/3. It's like they go in alternate. Okay, so if you switch the place, then you can remember better. It's like this is 2/3, 1/3, 2/3, 1/3, 2/3, 1/3. Okay, so this is the charge for the quark. Now, quark, remember I said earlier, quark is made of, it is the building blocks of all matter, right? So they make proton, they make neutron, they make all other, most of the particles that we see. So you can see on the composite particle, the baryons, which is made of 3 quarks, all of this, right? The first proton, you can see the bracket, this is made of 2 up quark and 1 down quark. Okay, 2 up quark and 1 down quark. So 1, 2, 3, 3 quark made of made proton. Neutron is made of 1 up quark and 2 down quark. So this is UUD, this is UDD. Okay, UUD and UDD. Again, this one you need to memorize. They will ask you, what is the composition of neutron? Composition means what is it made of? Okay, the question asks, what is the composition of neutron? Then you say, okay, UDD, there's 1 up quark and 2 down quark, right? What about this? Lambda, sigma, sigma, and this is omega. All this we do not need. I will scale down this one to only this 2. Okay, this one, all this, they will not ask you. Now, other than the quark, you have the anti-quark also, right? So the anti-quark is the one with the bar, this one. All these are the anti-quark. So the meson is made of 1 quark and 1 anti-quark. Okay, so it can be the first one, for example, the first one is up quark with the anti-down quark. Okay, the bar here shows is anti, up quark and anti-down quark. And all this complicated one, we do not need to see. This one, anti-up quark and a down quark. Okay, these are pion, kaon, and eta. Okay, again, meson, will they ask you this one? Okay, so far I have not seen question asking for this one. So far. Okay, but you need to know that meson is 1 quark and 1 anti-quark. Okay, boson. Now, boson, photon, boson, W minus boson, W plus boson, Z boson, gluon, Higgs boson, and graviton. Okay, all this on. Right, all these names, right? You can see all these names is very special. Okay, they just give it a name. You can give it any name you want. Actually, if you discover the particle, then you can use your name also. Okay, any name you can give it, whatever you want. Right, so that's why you see all this like strange, charm, all these names coming up. Okay, so for the composite particle, right, most of it are unstable. Other than these two, other than proton and neutron, they are considered the stable one. Okay, neutron depends, but relatively stable, and all the rest, they are not stable. They are not stable. And the boson, they are not really particle, okay, because they are like the force carrier. And, okay, so quark is the basic one, made of most matter, and then we have the lepton, the electron, and neutrino. These are the things that you need to take down. Okay, let me just get some space here. Is the internet okay so far? Let me do a quick check on the line first. Okay, looking good. Huh? All right, now see here. Here I will draw the structure of a proton. So let's say we have a proton here. inside the proton is made of up quark, and down quark, right? So here you have it up quark, and down quark. So if you look inside something like this, and all these three quarks, they are held by a force. Okay, so I would say the composition of the neutron, of the proton, is U plus D, right? UUD. Now, what gives proton the charge of +1? The overall charge of the proton is +1, right? So if I look at the quark, now you have all the charge for the quark, right? Up, down, strange charm. Okay, so you can work out the net charge of the proton. So let's see here. Let's check the how do we actually get +1 here is up quark is +2/3 E. Okay, the second up quark again, you have a +2/3 E. And then the down quark here is a negative, right? -2/3 E. Okay, the first two you add up, you get 4/3 E minus, oh, sorry, this one should be 1/3, yeah? -1/3 E. Okay, so 4/3 E minus 1/3 E. So you get +3/3 E, which is equals to +1, right? So +1 E. That is where you get the charge of the proton, +1. Okay, so this one, you need to know how to work it out, because in the exam, they will ask you to do it. They will give you like a unknown particle. Okay, they say, okay, it's made of up, down, up, or down, down, down. Then they ask you to find what is the net charge. Okay, so let's do another one for the neutron. Okay, let's see neutron. Neutron is up, down, down. Here, down, down. UDD. Okay, so +2/3. This is -1/3 E. Okay, down quark, and then -1/3 E. +2/3 E. This one I add together, I get -2/3 E. Okay, it's the same thing. This one minus this one become 0. So this has 0 charge. So neutron has 0 charge. How do they know that the neutron is made of all these quarks? Before the quarks were discovered, because before the quarks were discovered, right? They think that proton and neutron, they are smallest unit, and then also they found that the neutron is supposed to be neutral charge, right? The neutron is supposed to be neutral charge, but then they found that when they shoot the particle at the neutron, it's like this neutron behaves some charge. It has some charge behavior, even though it is neutral charge. But when they are shoot the particle at very high speed, shoot at the neutron, they see like the behavior of the charge appear. So they believe that there's something inside the neutron. Okay, so they began shooting more particles, break the neutron down, okay, to see what is inside, and then they found all this quark thing. Yeah. Now the forces holding all this together, what do we call these forces? The forces holding the quark together, we call it a strong force. Okay, these are the strong nuclear force. Strong nuclear force. The strong nuclear force is the force that acts between quark and antiquark. Right here, force between quark and antiquark. It is one of the 4 fundamental forces. What are the four fundamental forces in the universe? Not like tension, not tension, reaction, all that. We are talking about fundamental, the very basic. The first one being this one, strong nuclear force. That is the fundamental force of the universe. The second force is the weak nuclear force. Okay, weak nuclear force. Strong nuclear force is the force acting between quark. Weak nuclear force is the force acts on all fundamental particles. Acts on all fundamental particles. Okay, the strong one is only between quark, but the weak one is like all fundamental particle. Okay, the distance where the force is significant, this one is about 10 to the minus 15 meter. Very small, huh? Because you are talking about inside a proton between quarks. It's very, very small. So 10 minus 15. Any distance larger than this one, the force is nothing. Okay, it cannot act. Weak nuclear force about 10 to the minus 18 meter, like this. So we already have the two fundamental forces. What are the other two? Number 3. Okay, I'll write it down here. The third fundamental forces is the electromagnetic force. Any force that has to do with electricity or magnetism, or both, the interaction between electricity and magnetism, they are the electromagnetic force. These are the force that acts on charged particle. Okay, only on charged particle. And the distance where they act is infinity. What do I mean by infinity? That means even though the distance is very, very far, the electromagnetic force can still apply. Okay, it can still apply on the body, even though they are very, very, very far away. Okay, so this one has to do with the light, okay, electromagnetic wave, okay, all this. Now, but I don't think you have many chapter about electromagnet in your AS. I think it's when you go to the A2, you'll do like a lot of electromagnetic stuff. Okay, number 4. Last fundamental forces is gravitational force. This one is also infinity because gravity can act very far, right? Sun, solar system, very, very far, infinity. And gravitational force is on all objects, every single object in the universe. Okay, they can be affected by gravity. So we say that these 4 forces, they are the 4 fundamental. Okay, so these 4 fundamental forces has to do with our dear boson here. Okay, all these boson, they are like the force carrier, remember? So for the strong nuclear force, who is responsible for the strong nuclear force? The strong nuclear force is our gluon. Gluon is the one that giving the strong nuclear force. Weak nuclear force is like our W and Z boson. Okay, electromagnetic force. Okay, this one may be related to the photon. Okay, photon, like light, all that, but not limited to photon. Okay, related but not limited. Now, gravitational force. This one is with the Higgs, right? The Higgs or the graviton. Higgs and the graviton. Okay, I will give you a 5-minute break and we will come back and we'll continue. So we will come back at 8 sharp. Okay, we are back and we will look at some past year's question. Huh? Example 1, a nucleus of sodium 21 decays to form a new nucleus containing 10 proton and 11 neutron. Which leptons are emitted from the sodium 21 nucleus during the decay? Okay, we draw out the decay. We have Na2111 decay to form a nucleus. Okay, I don't know what is it. I'm gonna just put it X. 10 proton and 11 neutron. Okay, 10. The nucleon number will be 21. Okay, so plus this one is 11 and this one is 10. So the proton number has decreased. So this one must be E21. Why I know is E? Because this one is the same, 21 and 21. So it cannot be alpha or other thing. So it must be a beta. So 21 and this one is +1. What is this? +1? Electron with a positive charge. This is a positron. Positron is a particle or antiparticle? Positron is an antiparticle. Antiparticle. So that means this is antiparticle, then there must be a particle. What is this? This is neutrino. Neutrino. Okay, so if positron is an antiparticle, then this one cannot be an antiparticle. There must be opposite. So this is the particle, electron neutrino. So this is a beta decay, beta plus decay. Right? So which leptons are emitted? So which one are the leptons? Remember our lepton, the first group, elementary particle, the first on the left, right? You have the lepton and the neutrino and all these different thing, right? So answer is positron and neutrino. B. Okay, example 2, a neutron decays to form a proton. Which particle is not involved in the decay process? Okay, a neutron, so 1, 0, decays to form a proton, 1, 1, plus E, 0. Okay, balance the equation, 0, 1, this must be -1. So this is a beta minus. Beta minus decay, this is electron. Electron is a particle. So there must be one antiparticle, the anti-neutrino. So antiparticle, go back to the list I show on the board just now. You have a bar here, right? The symbol for the anti-electron neutrino. This is anti-neutrino. Okay, the question says, which particle is not involved in the decay process? Anti-neutrino, okay, this one is involved. Down quark. B, okay, down quark. Down quark again, quark makes what? It makes the neutron and a proton, right? Okay, it makes the neutron. This one is not related to quark. Neutrino is not related. The electron particle is also not related because they are the lepton, right? So only these two, the baryons, this one and this one, is related to the quark. So proton is made of UUD, right? UUD. So you have up quark, you got down quark are involved. So down quark is involved, up quark is also involved. So answer is C. positron is not involved. Okay, we go to example 3. What are the structures of the proton and of the neutron in terms of quarks? Okay, proton, UUD, neutron is UDD. Right, so proton is 2 up quark, 1 down quark. Out, this one out, 2 up quark, 2 up quark. Okay, down quark is 1. This one is not correct. Okay. Neutron is 1 up quark, 1 up quark, and 2 down, 2 down. C. Okay, example 4. During the beta minus decay, which change takes place to the quark composition of the nucleus that emits the beta minus particle, and which other particle is emitted? Okay, again, you can see the questions, they always ask beta decay, right? So that one confirm come out one, beta decay, okay, beta minus and beta plus. Okay, so this one is beta minus, beta minus, you have what? This one is N neutron, beta minus is neutron disintegrate into proton, 1 1 plus. Then you have this anti-neutrino. Okay, and then you got 1 beta minus, right? Beta minus. All right. So here we want to see what is the quark change. What does it mean by quark change? This all happened in the nucleus, right? This equation all happened inside the nucleus. So you want to see what is the quark change here. Before it was neutron, before it was UDD. Okay, so neutron is up, down, down. And then the neutron disintegrate into proton. So that means the proton has a quark of UUD. Here you have seen there is a change. There's a change. What changed? This D has changed to U. Right? Okay. So initially UDD, now is UUD. The down quark has changed to up quark. So down to up, this is correct. Down to up to down, this is incorrect. Okay. So these two possible answer. Other particle emitted anti-neutrino. Okay, so beta minus is a particle. So this must be an anti-particle. That means B is incorrect and A is the answer. Okay, number 5. What is the quark composition of a hydrogen 3 nucleus? 3 1. Okay, proton number 1 proton, neutron number 3 minus 1. We got 2 neutron. 2 neutron, 1 proton. Okay, 1 proton is made of UUD. 2 neutron, you got UDD, and you got another UDD. Okay, so total how many up quark? 1 2 3 4. 4 up quark and 1 2 3 4 5. 5 down quark. 4 5. This is A. Okay, so you just add up the total number of up and down. Now look at example 6. Some particles are a combination of 3 quarks. Okay, which combination of quark would not result in a particle with a charge of either 1.6 times 10 minus 19? This is basically E, right? Or 0. That means we want to find which combination of this does not give E or 0. Okay, if it gives E or 0, then that is not the answer. So let's see A. For A, now you can see up, down, down, right? Now you need to know what is the charge for each one. Okay, if you don't remember, then you cannot do this question. So up, okay, let's go back a bit. Up is what is the charge? Remember the placement of the particle in the list. We start off with the up. We start with up, down, and then we got strange, right? So we switch the position between strange and charm. Strange, charm, and top, bottom. Okay, so this one is plus 2/3. This is minus 1/3, and then same, alternate. Okay, plus 2/3, minus 1/3. So just remember the placement. Okay, so up is the first one. This is the 2/3 plus 2/3 E. Right? So down, 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 down is minus 1/3. So 2/3 plus minus 1/3 minus 1/3. What's this? 2/3 minus this. Okay, you get 0. So the first one, net charge is 0. Okay, B, up, strange, strange. So plus 2/3. Strange is plus 2/3. Wait, this one is, sorry, this one I should be, this one should be charm first, right? Okay, I made a mistake. This one I change, charm, strange. This is plus 2/3. This is minus 1/3, okay? Right, 2/3 minus 1/3 minus 1/3. Again, you get 0. Up, up, down. 2/3 plus 2/3 minus 1/3. What is this? 2/3 plus 2/3, 4/3 minus 1/3. You get plus 1. Plus 1 E is this one, is 1.6 times 10 minus 19. So this is also not the answer. Left only 1, so this must be the answer. So let's just find what is the charge here. This is 2/3 plus 2/3 plus 2/3. You get 6/3, 313, 32. So this is plus 2E. It has a charge of plus 2. So D is the answer. Okay, one more example, example 7. A hadron has an overall charge of plus E, where E is the elementary charge. The hadron contains 3 quarks. One of the quark is a strange quark. So the other 2 we don't know. Huh? State the charge in terms of E of the strange quark. Okay, so strange is minus 1/3 E. Okay, let me write this down again at the side. Up, down, charm, strange. top, bottom. Okay. Number 2, the other 2 quarks in the hadron have the same charge. By considering charge, determine a possible type of the other 2 quarks. So you want to find what is the other 2. How do you find this? Okay, so you know got 3, right? Got 3 quark, and then the net charge should be a plus E. I will write here plus 1. Okay, I'll just drop the E. And I know one of it is strange. So minus 1/3. The first 2, I don't know, I just put Q, represent an unknown, okay? But they have same charge, right? Same charge as each other. So I just write 2Q. Okay, 2Q minus 1/3 equals to the net charge 1. Okay, then I solve as usual. 2Q equals 2. This one, 4/3. Q equals to 4/3, divide by 2, you get 2/3. So Q, the charge is plus 2/3. What charge is that? What quark is that? What quark has a charge of plus 2/3? Okay, it can be up quark, it can be charm, it can be top, right? So you got plus 2/3 minus 1/3 plus 2/3 minus 1/3. So the answer is what? Answer, you can just pick one. Okay, you just pick the normal one, common one. You can say up, up, strange. Right? If you write charm, 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 strange, that is also correct. Or top, top, strange, that is also correct, since the charge are the same. Okay, moving on to the next one. Okay, we look at the last part. Okay, after I finish this, then I'll wrap. Classification of matter and antimatter. Now, just now I show you a table, right? Showing all the particles, okay, most of the particles. That is one classification. You have the boson, the fermions, the baryons, and the meson. Okay, that is one classification. Some of those are matter, some of those they don't have mass, right? So here we have another classification that we only focus on the matter and the antimatter. Okay, so here I will write like this. We do matter first. So matter 2, first you have the hadron, and then you have the lepton. The boson I did not put here. Okay, the boson and the quark I do not put here because this is another classification. All right. So hadron and lepton. Hadron here is okay. Sorry, let me move it up a little bit because I want to get some space later. All right, this one is the lepton. You can see the first just take the first letter. H stands for heavy. Okay? These are the heavy particles, and L, they are the light one. The lepton are the light one. Okay, so hadron, we got meson. This is made of what? Meson is made of what? 1 quark plus 1 anti-quark, right? And then we have baryon. Baryon are the heaviest one because they are made of 3. Heaviest out of all of this. Okay, baryon 3 quarks. And baryon, we got 2 types, proton and then neutron, right? Proton is, what is the quark again? Proton is UUD, and the neutron is UDD. Now, there's this thing called the baryon number, something like a nucleon number. Okay, it's a new term. So baryon number B, for the baryon, right? If they are baryon, then they have a baryon number of 1. Okay, very easy. The proton is a baryon, so it has a baryon number 1. The neutron also the same. If it's not a baryon, then the baryon number is 0. That means all the meson here will have a baryon number of 0. Okay, right. So that's the baryon number. So think of it like a nucleon number, something like that. Okay, then for the lepton, we have electrons, and then we have the neutrinos. Neutrinos. Okay, these are the matters. These are the matters. For the antimatter, take whatever is happening on the right side, you copy and paste on the left side. Okay, we take the opposite of it. So I'm going to draw here, I'm going to write antimatter. So the first one being antihedron. Okay, remember, right? So when you have a particle, there must be the counterpart of it exists. You have matter, you have antimatter. So you add up, become nothing, which is the origin of the universe. So antihedron, here we got first meson, so we take anti-meson. Same, the component, the composition is still 1 quark plus 1 anti-quark. Right, up. Then we also have anti-baryon. Anti-baryon, so we have, on the right, we have proton, neutron. This one you got anti-proton, and we got anti-neutron. What is the composition? Anti-proton. You see on the right side is UUD, right? That is the up quark, and down quark. So on the left side, I'm going to take U bar. What is this? This is anti-quark. Okay, remember your quark also got anti. So anti-quark, we take a bar here. This is anti-quark, anti-up quark, and anti-down quark. U bar, D bar. Right? This one, same thing. We take the same, but we add a bar. U bar, D bar, D bar. Here. Right. Second one. This is anti-lepton. First is anti-electron. Anti-electron is what? Anti-electron, other names is a positron. Okay, same thing. Anti-electron or positron, they mean the same thing. And then we have anti-neutrinos. These are the one emitted from the beta decay, right? All right, so this is showing the diagram, the classification for antimatter and matter. What about the baryon number? This one, the baryon number is 1, this is 0. If for the antimatter, you just reverse the baryon number. So anti-baryon will have a baryon number of -1. Anti-meson, it is not baryon, right? So there's still 0. Okay, there's still 0. What about the lepton? Lepton has a baryon number of also 0 because they are not baryon. So as long as they are not baryon, then they get a 0. Anti-baryon, anti-lepton also baryon number is 0. Now, other than the baryon number, right, we also have a lepton number. Only 2, okay? So only 2, so 2 new term. The baryon number and the lepton number. So the lepton number L, okay? So as long as it is a lepton, it has a lepton number of 1. So this one is going to be 1. The hadron is not lepton, right? So L is 0. Anti-hadron is also not lepton, so lepton number is 0. But anti-lepton, you have a -1. Okay, just flip the chart here. Let me make a table. Here I will put hadron divided into baryon and meson. And then we have lepton divided into electron and neutrino. Okay, so here I write a baryon number, and here I write lepton number, BL. So baryon this is 1, 0, 0, 0. Lepton, this is not lepton 0, not lepton 0. This is a lepton, yes, yes. So 1, 0, 0, 0, 0, 1, 1. This is for the matter. For the antimatter, then you just flip the charge. If this is +1, then it becomes -1. All the 0 remain as 0. Okay, now how they will ask this one? Okay, so let's say we pick one decay. We pick one decay example. We pick the most common one, always ask beta minus. Okay, beta minus decay. Let me write out the equation. We have a neutron decay into proton, beta minus 0 minus 1 plus, what is this? This is ND neutrino, right? 0, 0. Electron is ND neutrino is an anti-particle. Now, given this equation, we want to see whether the conservation of charge, the conservation of baryon number, and the conservation of lepton number. What I mean is that, for example, charge left must be the same as right. Baryon number, left side must be the same as right side. Lepton number, left side must be the same as right side. So all must be conserved. So let's try to write down here the Q, which means charge. Okay, charge. Okay, what is the charge of a neutron? 0, no charge. We draw an arrow. What is the charge of a proton? That's +1. The charge of an electron, -1, so plus -1. And the charge of the anti-neutrino, it doesn't have any charge of 0, 0 here. So 0. Is the charge conserved? Okay, +1 -1 becomes 0, left-hand side and right-hand side. So charge is conserved. Okay, see the baryon number. B, what is the baryon number for the neutron? Neutron, where is it? Neutron is in the baryon, right? So it is a baryon. That means the baryon number of neutron is 1. Okay, +1. Proton. Proton is also a baryon, so +1. Now, electron is not a baryon, so plus 0. And antineutrino is also not a baryon, plus 0. Conservation of baryon number, plus 1, same. Okay, conservation of lepton number. Neutron, is it a lepton? It's not a lepton, right? It's not a lepton, so 0. 0, this one, 0. And what about this? Electron. Electron is a lepton. So the lepton number is a plus 1. Now, the last one, antineutrino. Antineutrino is on which side of the diagram? On the left side of the diagram, over here, this one. Because it's antiparticle, right? So antineutrino, the lepton number is what? Minus 1. Minus 1. So plus minus 1. Okay, 1 minus 1, conservation of lepton number. So all these three, the QBL, we say, okay, the QBL must be conserved. Now, this is one way to write the decay. And I will show you another way to write the decay. Because sometimes they might not show it like this. They might show it the other way like this. Let me erase this table here first. Okay. Another way I can write this decay, the same decay is I can write it in terms of the quark change. Okay, what is quark change? Quark change. Here. Neutron, what is the quark? We look at the left side of the equation of the decay. Neutron is a quark up, down, down. And proton, our quark is up, up, down. What is the change in the quark? From down to up, right? So we only take the change. That means I'm going to write my equation as D down quark change to up quark. The rest is the same. Plus beta minus plus and D neutrino. Okay, so the neutron and the proton I change to this one. Sometimes they write it like this, the quark change. All right, so when they do the quark change, okay, so what do you do with the conservation of QBL? Okay, let's do it again. QBL charge. What is the charge? The Q, the charge of a down quark. Is it 0? Not 0, down quark. So remember your quark, the down quark, it has a charge of minus 1 over 3e, right? So I just write minus 1 over 3. Okay, because down quark is like 1/3 of a proton or a neutron, right? So which is 1 over 3. 1/3 of a baryon, because baryon is made of 3 quarks, 3 quarks. So here you only have 1 quark, the down. So it's 1 over 3 of the baryon. Okay. All right. Q is the charge is minus 1 over 3, and then up quark is a positive 2 over 3. Okay, so in case you forgot, let me write this down here. Maybe for some of you, you didn't manage to take it down just now. I'll write it here again. Up, down, charm, strange. And then we got top, bottom, plus 2 over 3, minus 1 over 3, plus 2 over 3, minus 1 over 3, plus 2 over 3, minus 1 over 3. Like this, right? So these are the charges. So just take here. Down is minus 1 over 3. Okay, up is 2 over 3 plus beta. Okay, beta is a minus 1. And anti-electron, anti-neutrino is a 0. Conservation of charge is the same. Okay, plus 2 over 3 minus 1. Okay, it's the same. This one on the right hand side is also equal to minus 1 over 3. Okay, charge is conserved. Now, what about baryon number? How do I know the baryon number of a down quark? The baryon number of a neutron, right? Of a neutron is 1, right? But if I only want a down quark, now baryon is made of, again, it is made of 3 quark, right? So if baryon number is 1, then the baryon number for 1 quark is 1 over 3. Okay, following? Again, the baryon number, any particle that is baryon has a baryon number of 1. But if I'm talking about the down quark only, which is 1/3 of a baryon, okay, because it's made of 3 quark. So the baryon number here, I'm going to write 1 over 3. Okay, arrow. This one is the same, 1 over 3. Plus, this is not a baryon, 0. This is not a baryon, 0. Okay, conserve. Last one, lepton. Okay, lepton number. Down quark, a quark is not a lepton, so 0, 0. This is plus 1. This is anti, okay, same as the P4, minus 1. Okay, anti-neutrino has a minus 1. Okay, so this is how you do it. The conservation of charge, baryon, and lepton number. Now, once you have this one, right, and we can create a, sometimes they'll ask you to draw a diagram called the Feynman diagram. Okay, I erase this one first. Here, construct a Feynman diagram. What is it? It's just a simple sketch, a simple diagram showing the decay. So the decay, I can show it in an equation, right? Or I can show it in diagram. So diagram is plotted with time axis. So we will draw an axis of time here going up. And then I will draw something like this. Now remember, we separate it into like upper and lower region. The lower region shows before decay, like the component before the decay. The upper region shows the after the decay. Okay, after decay. So it's like, what is the product? All the product from the decay, I'm going to write it up here. So I'm going to draw a diagram like this. First is before decay, it was neutron, correct? Here, we look at this example, the bottom right, the equation on the bottom right. Before decay, it was neutron. So I'm going to draw one arrow. This should be pointing upward like this. This represents N, neutron. Okay, the arrow is pointing up because the time is like this, right? Going up over time. So it follow the time axis. So going up, and then after decay, what do we have after decay? We have the proton and electron and anti-neutrino, right? So I'm going to draw the proton over here. Like this. This is the proton. And then I will draw this like a squiggly line like this. And then this is the byproduct. The byproduct is on the right hand side. This will be the beta minus. Okay. And then I draw another one. This pointing downward. This is the anti-neutrino, V bar. Okay, you see. Why the anti-neutrino is pointing downward? Because this anti-particle. So anti-particle, the arrow is opposite. Normal particle, they should point up. like the proton and the electron. They are normal particle, so they point up. So follow the time axis, right? And the neutron also you point up because we follow the time axis over time. But the antiparticle we point downward. Okay, so it is opposite direction. And again, you can see the beta and the antiparticle is on the right side because that is the byproduct. Our main product is the proton. I put it on the left side. Okay, so again, at the bottom part shows before decay, the atom before the decay, and upper part is the after decay, what you get after decay, right? So they are separated by this wavy line here. What does this represent? This is like, we label here W boson. W boson. What is W boson again? W boson is like the one that related to the weak force, the weak nuclear force, the W and the Z boson, right? So W boson is like the forces holding all fundamental particles together. That's why I draw it here, W boson, holding everything together. Okay, so this is how my Feynman diagram looks like. Okay, how my Feynman diagram looks like. Now, another type of Feynman diagram, okay, everything else is the same, but sometimes they want to draw like this. T, and then they will show the quark. This neutron is UDD, right? UDD, and this proton is UUD. What is the quark change? The quark change is D to U. That means I can show the quark here, one line, two line, one line, another line. Bear with me a little, like this, like this. This I'm gonna write UDD. Okay, it's the same thing. It's a neutron, right? But instead of writing the N, I put the UDD in. UDD, and up here, what do we get? UUD, right? UUD. But here, I'm gonna write UDU. Why? Because I want the one that is changing, I want it to be on the rightmost, which is this one. This and this. This is the change, right? The change is going from down to up quark. So I put it on the right side. This U to U doesn't change. D to D doesn't change. So this one, D changed to U. That's why I switched the position from here. I write UDU over here, up here, okay? UDU. Because I want to show the change that is at the third line. The third line should be connected to the squiggly line here. This line here, like this. Okay, so this one is going to be beta minus. Everything else is the same, doesn't change. This one is a anti-neutrino like this. This is, again, the same decay, but two different types of drawing the Feynman diagram. Okay, here I labeled W boson. This one is showing the neutron and the proton. This one is showing the composition, showing the quark and the all the quarks. Okay, and remember, the change should be the line connecting the wavy line, which is this third arrow here. Let me highlight it. Okay, this third arrow here, this showing the change of the quark. It should be connected to the wavy line.